All right, hopping in to a brand new chapter, chapter 15, chemical kinetics. There's a lot of math relative to some of the other chapters that we've done before in chemical kinetics. There's multiple formulas that you don't necessarily have to have memorized, but it might be helpful to have memorized. And there's some calculus that we're not going to do. We're not doing the calculus. Don't worry, no sweating about calculus. There's some stuff where we'll just say, and this happens because of calculus. And if you want an explanation for why that is, how they do those calculus, you can find examples on YouTube. There's lots of great videos about them. They'll show you the step-by-step of the calculus. That being said, let's talk about lizards. Lizards and other cold-blooded creatures are called ectotherms. You don't really need to know that, it's just for fun. Their body temperature matches the environment's temperature. So if it's cold outside, they slow down because they get colder. And if it heats up, then they can move around more easily. They like to sun themselves. Often you'll see lizards. If you see a lizard, it'll be out in the sun, and it might be doing push-ups. There's a fun video of lizards doing push-ups at the gym right after New Year. I thought that was fun. More recently, people were alarmed about crocodiles or alligators. I don't remember which it was, down in Florida or Texas, where it froze the lake. And they're like, wow, these crocodiles or alligators, they've got their snouts out of the water, and it's frozen, but somehow they're still alive. And it's like, that's what they do. This isn't a surprise. So ectotherms slow down, metabolism slows down. Unlike us, where we keep ourselves warm and our metabolism stays trucking. Part of the reason this works for lizards is the chemical reactions in their body also slow down. So their metabolism slows down. They start using energy less rapidly because of cooling down. And so they're able to survive, for example, if they're frozen under a lake, as long as they can breathe. So chemical kinetics, what we're talking about today, the chemical part, of course, chemistry, and kinetics, stuff moving around. It's factors that affect the rate of chemical reactions, like temperature, with the ectotherms. And the reason that we want to understand what affects rates of chemical reactions is so that we can influence them. We want to understand how the chemical reactions work, what are the things that make them tick, so that we can push the buttons and pull the knobs and levers when we need to control those rates. Right? We might have instances where we want to speed up or slow down a reaction rate. If we want a chemical to last longer, if we're pumping it into an environment, we want it to last longer. We want to be able to control the rate of any reactions that might be going on. So we'll want to slow down the rate of the reaction. That means our chemical is going to last longer. And rates are important for a bunch of things, including rates of fuel combustion. Like if you have a fire, today we can actually burn in Fresno County, so you're legally allowed to have a fire in your fireplace, unlike most days of the year during the burn season. Biochemical reactions are controlled by enzymes. Enzymes drastically affect reaction rates. And chemical reactions give us some information about how the reaction occurs. So those are all nice things. The rate of a chemical reaction is a measure of how fast the reaction makes products or uses reactants. Those are kind of analogous. We've got two examples. Up top, we've got a reaction with a fast rate. This reaction goes very quickly. It's done faster than our reaction with a slow rate. So we've got A, these long pills, and B, these little short pills that react to form C, the kind of oblong pills. And from frame 1 to frame 2, 15 minutes or whatever, we can see that we've got 4 reactants or 4 products already made. We go a little bit longer, we've got more products, and then eventually at this 45-minute mark maybe, it's all products, completely used up our reactants. In the example of our slow rate, slow and fast here are just kind of relative terms. In our slow rate, we're doing a similar thing, but instead we're going to these pink oblong pills. At 15 minutes, instead of having 4 of those oblong pills, we just have 1. We've got 2 after 30 minutes and 3 after 45 minutes. It's a much slower reaction. We still have plenty of reactant left over. Fast and slow are relative terms, qualitative terms. How do we define rates? The most common rate that we're probably familiar with is speed of a car, for example. A rate is one thing changing against time. It's like distance over time with speed of a car. The rate part is an over time with respect to time. So the speed is a rate. It's our distance traveled. For us, that's in miles. In a given period of time, we usually use 1 hour, but it could be seconds or minutes or days. So our speed, we could call that a rate of travel, is the change in distance, change here being represented by this delta. So the change, the amount of distance that we traveled, final versus initial, over our change in time, when we stopped versus when we started. And we can use that information over any distance to calculate an average rate of travel. How fast were we going from my house in Fresno to here? If it took me 30 minutes, we could do that calculation. We also have reaction rates. So let's say that we've got a gas phase reaction between hydrogen and iodine going to form hydroiodic acid. The change in concentration of the reactants is negative because the reactant concentration is decreasing. However, reaction rates are positive by convention. This is just how we've done it, or tradition. And so the rate is defined as the negative of the change in reactant concentration. So that's a fun little detail to remember. So our rates earlier for travel, it was the change in distance over the change in time. Here we've got a rate that's the change in the concentration of our reactant over the change in time. Remember that those brackets mean molar concentration of whatever's inside. And again, because it's a reactant, the reactant's getting used up. In order for us to have a positive rate, we're putting a negative sign in front. You might be able to think of this as like if you were thinking of traveling west as going a negative direction, like you put a grid on a map. If left is going a negative direction and right is going a positive direction, if you're traveling west, you might end up with a negative distance traveled, but it wouldn't make sense for you to have a negative speed, and so you would throw a negative in front of it to make it positive so that your rate of speed is positive. That's sort of what we're doing here. If that helps, hopefully it helps. If not, ignore me. Questions so far? Rate can also be defined with respect to the product of the reaction. Reactant concentrations increase, so the rate is normally positive and we don't need a negative sign. So reaction rate needs to be positive. And we're coming up with a rate. And our rate, in this case, we have a coefficient of 2 in front of HI. And so our calculation for the reaction rate is 1 over 2 times the change in concentration of HI over the change in time. Why do we have a 1 over 2? Yeah, it's because of the coefficient. We get that 2 from the coefficient. Why isn't it 2 instead of 1 over 2? We're calculating a rate. What are we calculating the rate for? For the reaction. So we're calculating a rate for the reaction. This is a conventional thing. It's helpful to calculate it for the overall reaction, so reaction rate, rather than calculating. We can also calculate change in concentration for our HI. That's not what we're calculating here. And in order for us to have a rate that applies, or we can apply to all of our reactants and products, we're taking out the coefficient part, the 2 part, to find that rate. And then if we had another coefficient, we would multiply our rate by whatever the coefficient is to get the rate of change for that thing. So that's why it's a 1 over 2, because this is the rate of the reaction. That might become a little bit more apparent why it's that way later on. I think we've got some examples, or at least one example that utilizes this. And I don't need to write that because it's coming up. OK, defining our reaction rate. The concentration of HI increases at twice the rate because of the coefficient of 2. That H2 or I2 decreases. To have a single rate for the entire reaction, we need to reflect the coefficients in that reaction. So that's, again, why we're getting this 2. We're dividing by it instead of multiplying by it. So again, this is rate of the reaction. It's not rate of change for HI. We can also graph stuff. So here's a graph of our reactants and our products. We've got one of our reactants graphed here in this green decreasing line. We've got our product in this red increasing line. On our graph, we have time on the x-axis, so going left to right, we're increasing in time. We're moving forward with the reaction. And our concentration is measured here on the y-axis. So the higher you are, the more of that thing you have. Reactant concentrations decrease with time in this case. Because we're using up the reactant. We're running out of reactant. We can't do these reactions as quickly. The product concentrations, oh, no, reactant concentrations always decrease with time. Product concentration increases, and in this case, HI increases twice as fast because of the stoichiometry in the problem. Because we have a 2 here, it goes up twice as fast. And we can calculate changes based on a graph. So looking at the change in y and the change in x our concentration and our time, we can make calculations of the rate through time. Our average rate of the reaction decreases as the reaction progresses. Our reactant gets used up. We can calculate at each of these data point steps. We've got a bunch of different time values on our first column, our second column, a bunch of different concentration values for our reactant, and then the changes in our concentration for each one of these steps, and the change in time is the same since they're evenly spaced. So our initial rate of the reaction starts at 0.018, and by the end we're at 0.0030. So this reaction slows down over time. It's starting out hot, but it uses up its fuel. It has less and less fuel towards the end. You can kind of think of it as running a long-distance race. You start off hot, and by the end, maybe you've used up all your fuel. You're really slow if you're not an experienced runner who paces themselves. We can also calculate an instantaneous rate of the reaction. So this is our rate at one point in time rather than an average. And we can find this from the graph. So this is the same graph that we saw before. And we just figure this out from the slope of the tangent to the curve at that point. So take any straight line and line it up so that it only touches one point of the graph. And whatever that rise over run is, that slope is our instantaneous rate. And then you might have to do the stoichiometry as well if you're doing it for HI. I believe we'll be doing this in one of our labs. We'll at least be graphing stuff in one of our labs this week. Here is our generic rate of reaction formula. So we've got lowercase letters, the A, B, C, and D. Those are representing our coefficients. In our example, that was 2 for the one product that we had. And we can calculate the rate based on any of those changes. So if we measure the change in concentration of A, B, C, or D, any of them, we can find the reaction rate as long as we know how the concentration changed, how the time changed, and what the coefficient for that chemical was. So that is convenient. However, this only works for one point in time. This could be an average if we're calculating from a starting point to an ending point, or it could be instantaneous. We would get that from the slope of a graph. And this whole thing, the rate, as well as what our generic equation looks like, would be great things to know. And again, that rate is the reaction rate. and we've got the negatives in front of the terms for our reactants since they're getting used up. Our change in the concentration is going to be negative. If we multiply that by the negative that we put there, that'll give us a positive reaction rate. You should never have a negative reaction rate, always a positive reaction rate. All right, forgot to block out the answers. That's fine. Consider this balanced chemical reaction. In the first 10 seconds of the reaction, the concentration of I- dropped from 1 molar to 0.868 molar. Calculate the average rate of this reaction in this time interval. So we are calculating this for iodide. So we'll find iodide in our reaction. And remember, our rate equals the change in the concentration over the change in time. There's a couple other things that we need for this formula. What's one of the two things we need still? The coefficient. We have a coefficient of 3. So we need a 1 over 3. There's one other thing that we need. Is this a, huh? The negative. Yeah, we need the negative because this is a reactant. So our equation for the rate for this reaction for iodide is here. And this change in I- and the change in time, we can substitute numbers in for those. So this is equal to negative 1 over 3. Our final concentration minus our initial concentration over our change in time, which was given to us as 10.0 seconds. Since we're just doing an average, if you somehow flip if you get the concentration things mixed up, it's not a big deal. It just won't cancel out your negative. You'll just have to remember to pull the negative out. It'll be the same number though. So this is equal to negative 1 over 3. Our change in concentration is negative 0.132 molar. Over 10 seconds, we can plug that into our calculator. So we get the expected number if you've taken a peek at the top right-hand corner. 0.00440 molar per second. Again, this is an average rate. So this doesn't mean that this was the rate the entire time along this 10 seconds. This is kind of like if I said that my average speed driving here from my house was, let's say it was 50 miles per hour. That doesn't mean I was driving exactly 50 miles per hour the whole time, because that would be crazy driving out of my neighborhood at 50 miles per hour. Right? I was driving slower at some points. I was driving faster for most of it. But on average, just from the start to the end, that's what our rate was. Questions? All right, determine the rate of change in the concentration of H+ during this time interval. So our reaction rate, we figured out in the previous problem, that was A. And we want the rate of change in the concentration of H+. So we're looking for delta H+ over delta T. So it'd be helpful for us to write out what our reaction rate would be for H+. We know what our overall reaction rate is, and so we can write in the rest. It's the same thing that we did for the previous problem. Minus 1 over 2, because of our coefficient of 2. Change in the concentration of H+ over change in time. And we'll take this and rearrange a little bit. If we multiply both sides by -2, that'll get rid of our -1/2 on the right side. So we get minus 0.00880 molar per second equals change in concentration of H+ over the change in time. What does this mean? A couple of things that it means. We've got a negative in front of our change in concentration. That means our concentration is going down. And we have a specific value for what the average change in concentration was during that time. You might have also noticed that, yeah, we can do this like really mathy version of it, but if you just take the reaction rate, multiply it by 2 for the coefficient, and then remember that its concentration is going down, the negative part, it's pretty easy to get the answer from the reaction rate. And we could do that for any of these reactants or products. For example, predict the rate of change in concentration of hydrogen peroxide and I3- during this time interval. Let's give that a shot. All right, two chemicals that we care about. In this case, the hydrogen peroxide, H2O2, and I3 minus. They both have coefficients of 1, easy peasy. One of them is a reactant, the other is a product. We can write out our definitions of these. Change in concentration of H2O2 over change in time. This one has the negative sign in front of it because this is a reactant. For I3 minus, it's a product. We're not going to have a negative sign in front of it. So delta concentration H2O2 over delta T is negative reaction rate. So over this period of time, our hydrogen peroxide is decreasing in concentration at that rate. And for I3 minus, it's increasing at the same rate. If we had done this instead of for I3 minus, if we had done it instead for H2O, how would we change this number? What's different? The coefficient. So we would just multiply it by 2, leave it as positive, and that would be our H2O. So for H2O, it would be 0.00880. Keeping it as positive because it's a product, so its concentration is increasing. All right, for the reaction, A plus 2B goes to C under a given set of conditions. The initial rate is found to be 0.100 molar per second. What is the change in concentration of B over change in time under the same conditions? Any ideas? We've got a guess for C. Any other guesses? We've got a guess for A. Any other guesses? It is one of those two. So nice work. Let's figure out which one it is. So our rate is 0.100 molar per second. Our definition for finding that rate from B would be it's a reactant, so we need a negative and a 1/2 because of our coefficient of 2. And then the change in concentration over the change in time. To undo this negative 1/2 and get it to the other side of the reaction, we'd multiply by negative 2. So negative 0.200 molar per second. Change in concentration of B over change in time. So if we have the rate, you take the rate, multiply it by the coefficient. If it's a reactant, it's negative. If it's a product, it's positive because they're going down or increasing respectively. So that's how we would get C, either of those two methods. You don't have to write out the whole definition every single time. If you can do it in your head, then that's fine. So for A, it was just got the two the wrong direction. Questions? All right, we're having a good time. So measuring reaction rate. For us to measure reaction rate, we need to be able to measure the concentration of at least one component as a function of time. And there's two ways we can do that. If it's a very fast reaction, we would probably want to do continuous monitoring. There's a bunch of ways to do that. Or very frequent sample analysis. If it's a reaction that occurs over a very long time, like if it might take a day or a week, you're not going to want to sample that continuously because that's a lot of data, that's a lot of instrument time, that's possibly a lot of your time. And so sampling at various time points might be beneficial. Right, you sample every 4 hours, or if it's something that's like 2 weeks, you might just sample once a day. Makes things a lot more convenient, and you're not hogging an instrument for 2 weeks or longer. There's some ways to do continuous monitoring. One of the ways that you can do it is polarimetry. A polarimeter works by passing light through a known length of a sample, and there's certain molecules, depending on how they're oriented, depending on which version you have, that will turn light as light passes through it. And so you can measure with a polarimeter how far the light is getting turned, and you know the distance that it was traveling, and you can do some calculations to figure out, okay, this must be the concentration of the thing that turns the light right or left. And you can watch that angle decrease or increase depending on if you're using up or creating that particular chemical. I think there's decent odds we'll get to polarimetry later in the class. You could also measure, for example, total pressure if you've got an equation that has different numbers of moles of gases and is roughly ideal. So for example, if you've got N2O that's going on to degrade to N2 and O2, you could have a pressure gauge that's either hooked up to something that monitors it, or you could just take a video or something. And we've got 2 mole equivalents on the left side, we've got 3 mole equivalents on the right side. So as this reaction proceeds, we're going to end up with more moles of gas. And so our pressure should increase if our volume is staying constant. So we do this in a constant volume environment. You could probably also measure the volume of the container, but that would probably be more tricky unless you've got a nice piston set up. And then spectroscopy is another way that you can do it. So spectroscopy uses light, either a particular wavelength, or you can do a range of wavelengths that you scan through for things that absorb light. There's other related methods that you can use for things that fluoresce. So you hit them with UV light, and then they produce another light that comes back at you. Here's a real basic version of how a spectrometer works. The meter part here means measuring. And the spectro like a spectrum, so we're spectrum measuring. So you would have some light source, and you'd have to have a very particular light source, otherwise this wouldn't be very quantitative. You run that light through a slit so that you get a nice beam of light, and then you can use a prism or some other method of spreading that light out into the full spectrum of light. And you can rotate your monochromator to select for the light that you want. That's what the little black rod sticking up the top is. So it's kind of like rotating a prism. You're changing which part of the rainbow is hitting the sample in this case. So you would run that so that this light passes through the sample chamber. And some of that light might get absorbed. It might just pass all the way through. And in this case, it would change over time. And then you hit a detector, something that measures the amount of light that's hitting it, and your computer logs that data over time. We'll be doing something sort of like this in our lab today. Questions about how any of that works? Again, this is a very bare bones, very surface level, how a spectrometer works. And you might do this for a reaction with H2 and I2. Iodine is violet, H2 and HI are colorless, and so you could see as this reaction proceeds, your I2 gets used up. Color becomes clearer over time. So you could maybe measure the amount of violet light that's coming through or something like that. And that would be great if you had a short run or if you wanted initial rates. If you had something that took a really long time, you might want to do periodic sampling, which could be just 30 minutes apart or an hour apart, depending on how quick your reaction goes. So you're going to take an aliquot. An aliquot is basically just a sample. It's a small part. You'd pull off an aliquot at specific times during the reaction, say at 4-hour intervals. Regular or planned intervals. For example, if you work a 9 to 5, you might come in and at the start of your shift, you pull an aliquot off. 2 hours later, you pull another aliquot. 2 hours later, you pull another aliquot. Just the whole time that you're there, and then you come back the next day. Or you have somebody else pick up when you're not there to do your sampling. Or if you're lucky, you have an automatic sampler that'll do it for you. So you pull off all these samples, hold them as a batch or run them individually, and you do some form of quantitative analysis. Quantitative versus qualitative. Quantitative gets you a number. In this case, concentration. Rather than like for some of the spectrometer stuff, you might be able to look at it and like, well, it's lighter violet than it was 30 minutes ago. That might be helpful, like yes, a reaction's proceeding, but you don't know how much lighter it's getting. So we want quantitative analysis, need quantitative analysis to do these. Some techniques that you might use, you might do a titration. That's a lot of titrations. That would work really well for some things. You could do a gravimetric analysis, like a density analysis, or you can use some form of gas chromatography that measures the concentrations in the mixture. A gas chromatograph, we're looking at a very pared down version here. A gas chromatograph has a bunch of components to it. It has a carrier gas supply. This carrier gas supply usually helium, oftentimes also hydrogen, sometimes nitrogen. You'll have running through this column. The column is sticky on the inside for chemicals. It runs through at a set flow rate so that you know that everything's traveling roughly the same rate. you've got an injection port. You'll put your sample into the injection port. If you're lucky, you've got an auto sampler that'll do the injections for you. So you put in a known amount, it hits something really hot, turns it into a gas. All these things get turned into a gas, and the column coating material is sticky in a particular way. So some of those chemicals will stick a lot. They'll take a long time to go through. Some of those chemicals won't stick at all, and they'll basically just run straight through. So because of the way that they interact with it being different, you kind of separate out all of the chemicals in the column. And then when they come off in your detector, the things that didn't stick very much will hit first. And then it might be a gap of just waiting for those things to unstick from the column and come through. And then you'll get other sample peaks that come through. That's more of an in-depth analysis than you need. If you want to know more, I've done lots of GC stuff.
So every peak is a sample?
If you've done a good job of setting up your instrument parameters, every peak is a different piece of the sample. So we might have 50 different chemicals in our mixture. Maybe we only care about 2 of them. We might get 50 or 100 peaks coming off. Or, depending on our sensitivity, it might just be the 2 things that we care about if the concentrations are high enough. So every peak that would come out on our plot is a different chemical. So the column separates chemicals in the aliquot. Read sample. And detector, there's lots of different detectors. Just converts those chemicals into a signal. And if we did things properly, every peak, every one of these bumps is a different chemical. In the sample. So this lets us tease apart all of the different chemicals that show up in our sample. You don't really know how, this is more in-depth than you need to know. I like this stuff, so that's why we're going more in-depth. Questions? All right, more fun stuff. We also have rate laws. So we learned earlier how to find our reaction rate, and we also have laws about our rates. So this shows a relationship between the reaction rate, which we saw earlier, we're still going to be using that, and the concentration of the products. For a very simple reaction where A turns into products, the important part here is that it's just one reactant. So for this situation, our rate is equal to K, which is our rate constant. That's something you would find experimentally, times the concentration of A raised to some power. We are going to go over primarily the simpler rate orders. So the 3 orders that we'll be talking about, order of the phoenix, order 0 order. So if n up here is equal to 0, K times the concentration of A to the 0 power, anything to the 0 power turns into 1. So it just equals the rate constant. So whatever the rate is, just the rate constant. It doesn't matter how much of our reactant we have. This will proceed independent of concentration. So it'll be the same rate the whole time that it's going on under those conditions. If it's a first order reaction, then the rate of the reaction is directly proportional to the concentration of A. So as we start using up our A, our concentration of A decreases and our rate decreases. And we also have second order and higher orders that are also possible. So for our second order, for example, rate constant times concentration of A squared. And since the concentration of A is squared, we'll have a higher dependence on the concentration. It'll behave differently. It's not linear. It'll be a little more wonky. And you can have third, fourth, fifth possible orders, maybe. You could also have like a 1.5 order in some cases. We'll see stuff like that later. These are the three important ones to know. The way that reaction order affects things we can look at in these plots. So we've got two different graphs. Our graph on the left, we have time on the x-axis, so left to right, we're moving through time. And we have the concentration of A over time. That's what we're looking at. So we're starting off with 1, like 100% of our reactant. For our zero order reaction, the concentration just decreases at the same rate the whole time. We get a nice straight line. For first order, it decreases, but the reaction slows down, and so we use less and less, and this will eventually taper down to 0. For second order, the reaction rate decreases more. It looks more like an x squared plot, kind of the curve that it's got. Our other graph, we now have the concentration of A as our x-axis from 0 to 100%, and our rate is on the y-axis. For zero order, at every concentration, rate is the same. It's zero order. It doesn't depend on the concentration. For our first order reaction, we've got a 1-to-1 relationship between rate and the concentration of A. So we get a nice straight line. And then we've got our wonky one, our second order rate, that's doing a curvy thing. If I were making these are graphs from the book, I would have probably flipped the concentration of A. So if we look from the right-hand side of this graph, up in the top right corner, looking at this red line, our first order, as we move right to left, decreasing our concentration, our rate also comes down. I think that's the better way to look at it. So starting from up here, decreasing our concentration of A, our rate also decreases. Linear relationship between those two. Our zero order reaction, I already wrote this out earlier, but our rate is independent of reactant concentration. So for that n value that we saw for our rate, we put in a 0. This A0 term disappears. So our rate is just the rate constant. And our image here is sublimation. I don't know how it's sublimation, but apparently it is. And that would be an example of a case where we get a zero order rate. I'm assuming that this is a block of ice, and as this block of ice gets smaller. That's water molecules popping off of the surface of the ice. The surface of the ice is going to be roughly the same size no matter how many pieces of ice you lose through sublimation, and so the rate doesn't change. Because even though you're losing some, you've got the same surface area, only the ice on the outside can sublime. Similar idea with some of our solution stuff for dissolving things, KSP values and stuff. Our solids are ones. It's a similar idea to this. Okay, enough rambling. First order reaction. In our first order reaction, our N equals 1. So we get this rate equals K concentration of A. And rate and concentration are linked. So rate will decrease if concentration of A decreases. We also have our second order reaction, where our N equals 2. And since our concentration is now squared, any change in A is going to be magnified in the amount that it changes our rate. For a particular reaction in which A goes to products, doubling the concentration of A causes the reaction rate to double. What is the order of the reaction rate? Our options are 0, 1, or 2, where rate equals K, concentration A, to the order number. Any ideas? Got a guess for B? Any other guesses? Great, it is B. It's B because we've got a one-to-one relationship. We doubled the concentration, and that caused the reaction rate to double. So let's look at rate equals K, concentration A. If we plug in 2, whatever, for A, that 2 will come through and we'll have double the rate. So we get double the rate. If we have a 0 concentration or a 0 order, there's no concentration of A term here. Right? So nothing that we do to change the A value will change our rate. If we had it second order, and we plug in our 2A, that term gets squared, and so it would be 4 times the rate instead. Hopefully that was helpful and not just confusing. If we want to determine reaction order, you have to do an experiment to figure out what the reaction order is. And there's a couple ways to do it. The method of initial rates is you look at the very start of the run, start of a reaction at different concentrations. This is convenient because you just start the thing, and especially if it's got like a long reaction time, you don't have to sample it at multiple points. You just start the reaction, figure out the rate right away, either with 2 really close samples, if you're good at measuring rates, or some other method. In this case, we've got data, magical data. So we ran this several times. We're looking at the initial concentration and the initial rate. And we can determine the reaction order and the rate constant. There is a, what was I doing? So our rate is going to be equal to some k value times our concentration, in this case of A, raised to some n power. And for me, I just look at it and see if we double the concentration, what happens to the rate. And that would be how I would select this. There's a more mathy way to do it, where we've got an initial rate and a second rate. Not to be discounted, still important. And you can take these two things and divide them. To help you figure out what's going on. Some cool things that happen here. The k's cancel out. And we can consolidate this. Let me rewrite it. Rate 1 over rate 2 on the left side, concentration of A the first, raised to some n power, concentration of A the second, raised to the same power. Since they're both raised to the same power, we can pull out the n. So that will turn into A1 over A2, parentheses around that, and not 2, but n. And we can use this to tease apart some of our reaction rate stuff. So we'll take 2 data points. I'm going to pick the first 2. And I might have got my, yeah, it doesn't really matter. I'm going to put the bigger number on top so that we've got positive numbers. So our initial rate, 0.030 molar per second over 0.015 molar per second. That's a 2. If we simplify. And we've got 0.20 molar over 0.10 molar, which is also 2, raised to an n power. So 2 equals 2 raised to the n power. What does n have to be for 2 to equal? Yeah, n is 1. So this is a first order reaction. And that should go a box up. If you don't want to do that, and if you know your reaction orders, for a 0 order, the reaction rate doesn't change. Our reaction rate, we see in the second column, changed with respect to concentration. So it's not 0 order. We can look, okay, we doubled the concentration. If it's first order, we get a 1-to-1 relationship between our rate and our change in concentration of A, so we expect it to double. That's what it did. That meets our first order definition. If we doubled it, doubled the concentration, and the rate quadrupled, 2 squared, right, then that would be a second order. So you don't necessarily have to do this, but it might be helpful. Okay, so that's one way that we can come up with the reaction order. And we need to figure out the rate constant. The rate constant is K, the lowercase k. So our first order rate law, rate equals K times the concentration of A. So K equals rate over concentration of A. You can use any of those initial rates and concentrations. I'll use the top one, 0.015 molar per second over 0.10 molar. Our rate constant is 0.15 inverse seconds, because our molar units canceled.
We don't have to worry about the end there, or no?
So we figured out already that it was first order. And so the n in this case is 1, so I just omitted it. Yeah. So you would have to use whichever rate law is consistent with your reaction order.
So if it was like second order, we would leave the 2 there.
Yeah, if it was second order, then we would have a 2. And if it was 0 order, then, well, we already have our rate constant. Other questions? Cool. So for determining reaction order, this is that thing that I used on the previous slide. And I showed you how to simplify it. I'm going to rewrite it here, because I think that the way that it's written in this slide, which is probably the way it's in the book, is not the most helpful. Whereas this kind of simplified form lets you put in numbers right away, and you can figure out what your n is. Like I was saying previously, the other way you can do it is if the rate doesn't change with respect to the concentration, that's 0 order. Rate doesn't depend on concentration of A. There's no concentration of A in our rate law. And for second order, when we double our concentration, we quadruple, or 4 times, our rate. So rather than being 1-to-1, it's squared. Second order. Our rate constants have units that depend on the order. Rate is always molar per second. So K has units that give rate as molar per second. So in practice, what this means, for our 0 order, this A, concentration of A to the 0 power, we can get rid of that. In order for our rate to have units of molar per second, It's only K on the other side, so what units must K have? The same units. Because it's the only thing on the other side. For our first order rate, as always, has molar per second. K has some units. Concentration of A has units of molar. So we've already got our molar on both sides. K has to take up filling out this per second part. Inverse seconds or hertz. And for our second order rate law, rate still has units, or needs to have units of molar per second. Doing the same thing, K is equal to something, and A squared, concentration of A squared is molar squared. If you rearrange it, one over molar times seconds is K, so K has units of, as we might often see it, inverse molar, inverse seconds. Very fun and not confusing at all. So you might sometimes be able to figure out what the order is based on the units. And again, this is just from K picking up the balance to give us rate with meters, or sorry, molar per second. Any last questions before we wrap up? Because we've hit time.
You can write either or, right? Like inverse, or you can write 1 over S.
Correct. Those are equivalent. All right.